Yeah, and the due date's gonna be December 10th. It was originally the 8th, but I felt like we're definitely not finishing it all today, so I moved it over to a week away from Wednesday. Oh, that was feedback. Ignore that. Welcome back, folks. Looks like it's about time to start. And welcome back from the break. I hope you all had a restful break, didn't have to work too hard. So we should probably just sort of warm up slowly. It's been a while since we've done statistics. For the announcements, we're just about done with the course. We do have a good amount to do in section 15.3. We're going to do 3 big examples for hypothesis testing. Then in section 15.4, it's just more hypothesis testing. The only difference in that section, the last one for the whole semester, is that the data is quantitative. So all the work we did about thinking about hypotheses in 15.1 and actually doing them in 15.3, it's going to feel kind of very similar. Slightly different formula for the test statistic. But that's what happened in chapter 13. Once we got good at the confidence interval formula, once you go into quantitative data, you're just changing from p hats to y bar. Your standard error became slightly different. It became easier, in fact. So same idea in section 15.4 here. Well, we didn't have a quiz that we assigned going into the break, so there's no quiz that's going to be due this week. I'm going to post one last final quiz for this course, and it's going to be based off this kind of problem in section 15.3, just doing another hypothesis test in quantitative data. But any questions or comments so far? Okay, well, welcome back once again, and congratulations on almost being done with the course. Week 14 is going to be kind of a normal week, but once we get into week 15, Monday, we're going to pretty much be finalizing our work. And I want to spend most of Wednesday and all of Thursday just reviewing for the final exam. So we're just about done with the course material. As far as the final exam, here's the information about what we've got going on. The official time is 8 p.m. to 10 p.m., which is kind of brutal. I'll put in an extra comment here. We could probably just put that in right now. The official time is 8 p.m. to 10 p.m., but if that doesn't work for you, there's also another time slot that we're giving. This can also be taken between 5:30 p.m. and 7:30 p.m. I'll be here in this classroom for both time slots. So pick the one that just works best for your schedule. If both of them are available, then just think about when I'm probably more awake and aware, better able to do statistics. And you'd be surprising what the answer is to that. I'd say the best time to do a final exam is likely to be the best time you actually do statistics in the first place. The best time you've been studying for this course is the best time to do the exam. So try to pick the closest time slot, and I'll be available on either one. It'll be a long night, but we'll get through it. These versions 1 and 2 are problems that you've seen before. These are essentially the old updated final exam problems, but now they go all the way from, say, the very start, chapter 1, to the very end. This is a 49-page document, so you might want to just download it instead of printing it out. But it goes all the way to the very end, 15.4, doing the hypothesis test. So version 1, version 2 do the same exact thing. But if you want to get a feel for what does a 2-hour exam look like, it's not going to be a 50-page exam. This is a real sample final exam, and the solutions are down below. That was given the last time I taught this class, which I believe was just last year. So this is what a real final exam will look like. You can take a look at this document, practice it to see how it goes, and get a really good sense of how prepared you are for a real 2-hour exam. My exam isn't going to be exactly like this. The problems are going to be different, but it's going to be the same kind of stuff in spirit. If you can get through this exam, then you're prepared for the real final exam as well. Well, we'll talk a lot more about the final exam, especially next week, but any questions at all, folks, with where we're at or the upcoming final? Okay, well, let's jump back to our penultimate section, 15.3. Let's get back there. There we go. So we're on example 2. We're in the first full set of problems getting through these notes. First example was kind of a preview of how the formulas go together. And last week, before going into the break, we finalized example 1 to take us to this section right here. This is now the full set of official formulas for doing the so-called large sample test for population proportion. We'll briefly check conditions 1 and 2, that we have at least random data, but potentially a representative sample that represents the population. Condition 2 is going to tell us what's a large sample test, so we'll know by condition 2 if our sample size even meets that benchmark, if it's large enough. Here's where we have to be really careful starting in this section. If you're taking a look at how things worked in section 13.3, hang on, let me figure out how to move that. Things suddenly get a lot different. And 13.3 had this information. Part 1 is saying we need to check if we have a random sample or at least a representative sample. Then the sample size is large enough if the number of successes in the actual sample and the number of failures together were at least 10. But notice that p-hat is different. Here, for the sample test, hypothesis test, it doesn't matter how many successes or failures you have in the sample at all. It's totally irrelevant. What does matter is when you go and find the hypothesized value from the context, write your null and alternative hypothesis, it involves that value p naught. We've been making a big deal out of it as we went, always color coding it in that same color. That value gets used here. If the null hypothesis is true and you gather sample size n, this is how many successes we would expect to see from a sample size n. And this is the number of failures that has to exceed 10 on both. The test statistic tells us how far the data, p-hat, is away from the hypothesized value in terms of standard deviations. So it's an ordinary z-score, like we mentioned before. But the standard deviation is also tricky because it's different than the standard error. Standard error involves p-hat when we go to compute it. But why is it so different? It's because when you do a hypothesis test, you immediately assume the null hypothesis is true. You have a value for the population proportion p. And if you have that value, you also have the standard deviation. You know everything through the central limit theorem now about that population. So hypothesis testing gives you a pretty big leverage once you make that null hypothesis. So we'll again harp on those values as we go through the notes. Trickiest thing again about the hypothesis testing is saying what the parameter p is in context, forming the null, and then coming up with the alternative hypothesis. It's either going to be the right tail test, the left tail test, or the two tail test. This is really just going back on what we did in section 15.1, looking at those 3 different tests. But the context tells us exactly which test to run. From that test, we go to this side of the chart and we just use a normal CDF process to get the p-value. Once we get the p-value, the context will tell us what the significance level alpha is, and we make a decision based on its size. A small p-value, smaller than the significance level alpha, the problem must state, will tell us that we're rejecting the null. We found evidence that the alternative, whatever it is true. And a large p-value, this is the heartbreaking case. It could happen to you if you know you might run a statistical problem at some point in your program of study. If this ever happens, it's just as important to report you have failed to find significant statistical evidence that the alternative hypothesis, your hypothesis you're trying to find evidence for, is true. But when that happens, we have to be honest and say when we lack the evidence, just as when we say we found the evidence. So we'll come back to this table again. And that's a lot of information to put together. The next 3 examples are just going to walk through those essentially page and a quarter pieces of information. Any last questions or comments, folks, before we take a laser close look at each parts of these in context with a problem? Okay, well, here's where we essentially left off right before going into the break. Here's what a full problem could look like. These are pretty similar to how they look like in the homework. I think the only big difference is I'm only asking about 2 conditions, the randomization represented sample condition, and if the sample size is large enough. But aside from that, this is about what a question is going to look like in the homework, other than the homework is sometimes in certain parts multiple choice. This is maybe more similar to what an exam field could look like for a question. So it says, to start off with the context, the Substance Abuse and Mental Health Services Administration conducts a survey on drug use by type of drug and age group. So that sets the stage for the data. Results are published in National Household Survey on Drug Abuse. And getting closer into the context, it tells us next, according to that publication, 13.6% of 18 to 25-year-olds were current users of marijuana or hashish in the year 2000. So that looks like that's our big context right there. We're looking into a population, young adults, 18 to 25 years old. I'll just say briefly marijuana users or THC users. And specifically, this was a study in the year 2000. Now it says a recent poll. No actual information here. So I think this is the made-up data part of the problem. Well, it gives us a good statistical problem to work with. We have a recent poll of 1,283 randomly selected 18 to 25-year-olds. That looks like a sample size. So we can now say, this is our summary information. N equals 1,283 for the sample size. Revealed 205 currently use marijuana or hashish, however you pronounce that. That sounds like the success in this study. The moment they started giving us a percentage and we noticed there's no sample mean or sample standard deviation, we have categorical data. Our categorical data we're handling in this class only has two outcomes, success or failure. And this looks like the success. So let's highlight this. That's a bad way to highlight it. Let me try again. So we have successes here, which means 205 successes in the sample. That doesn't help with the conditions, but it'll be used later on in the test statistic. Let me just fix my penmanship there. Now, in our hypothesis test, critical thing is knowing exactly what the parameter is, but we also have to know what is the hypothesized value. The hypothesized value is the thing that's going to go here in the null hypothesis. H naught P equals P naught. But sometimes it's easier to think about the alternative hypothesis first because that's the research question. If this is your data and this is your study that you're conducting, the hypothesis you make is encapsulated right here. Sometimes you can identify the research question just by a simple question mark. That's a get dead giveaway. That seems to be the big question of the study, the alternative hypothesis. The question here starts by saying, did the data provide sufficient evidence to conclude that the percent of 18 to 25-year-olds who currently use marijuana has changed since year 2000? That absolutely sounds like the major research question of the study, which means it's the alternative hypothesis. So this whole statement right here is the research question. In other words, it's HA, alternative hypothesis. So we can see that it's essentially this, but we have to write out what is P specifically. I wrote this just once. It could have been a left tail test or a right tail test. Not equals means a two tail test. But that seems to be the case right here because the question is, has it changed? Is it above, below, or do we have any evidence of a difference of whatsoever? So the words has changed. Let me just underline it. Means this is a two-tailed test. So we'll be using the not equals, the same thing we see here in that alternative hypothesis. That's given us a whole lot so far. We're missing one major thing, the hypothesized value P naught. Anyone see what it would be in this problem? It is, good call. Sometimes you can tell what the hypothesized value is just based on time. If we're comparing something that happened historically, year 2000, about 25 years ago, to something more recent or in the present. Or maybe the hypothesized value came something like geographically. Maybe we're comparing the state of Idaho against the state of Alabama, for example. But yeah, that 13.6%, it mentions the successes again, current marijuana users. So that came up again. And the question was, is the percentage of current marijuana users among that age range different? Has it changed since that year? So that's the P naught value, the hypothesized value. P naught equals 0.136. We definitely want to convert that into a percentage to make our formulas run through clearly. But this gets us set up to run through all parts of the hypothesis test. We'll scroll up a couple times just to look into key elements of all this. But for where we're at so far, this is the exact thing you would have done right up to this part right here, highlighted. If you're doing a confidence interval, you need to know what the parameter is in the very first place. We'll go beyond and also state the null and alternative. That's just referring to H naught, HA. Let's scroll to about that part. Well, we're pretty much through with the setup, but let me look into one thing. It said, choose a level of significance. That was the thing I was looking for, the significance level alpha. I think this is going to be kind of rare for an exam question or a question in MyLab statistics will just tell you the level of significance that you're going to be using. Maybe on a quiz, I might make this an open question where you're going to choose it yourself. But that's kind of a weird question because you would have to go back to, say, 15.1. This is just really a review on what do we mean by a level of significance. And this is a good point to look into. Good spot. Hang on. Where do we, that wasn't this part right here. I think it was maybe this part, the same notes, 15.3. Sorry, it was a long break, it turns out. The significance level alpha, that one that we have to choose in this problem, is just a level of evidence, essentially. If we were doing a 90% confidence interval, we would pick a significance level alpha as 0.10, or vice versa. If we pick a significance level 1% or 0.01, that means if we did further analysis, it would have to be a 99% confidence interval. So when it asks you to choose one, when it's up to us, typical values would be larger than or equal to 0.10 up to about 0.01. I mean, they can be smaller, but that would be, say, high stakes research where making a mistake, the wrong conclusion could be very, very damaging. These are the common values, and it'd be very unusual to make it larger than a 0.10. Probably just bad practice in a certain sense. So I'll leave it up to you folks. Should we go for a high level evidence, 0.01? Middle of the road is 0.05, or low level evidence, like a 90% confidence interval, 0.10. It's the amount of evidence we're going to need before we reject the null hypothesis and say there's a real effect going on in our data. We have evidence of the alternative. Let's maybe start here. Let's write out what alpha is. Any volunteers for a direction to go on this one? Good call. If we're not sure, if you don't have any strong opinions one way or another on this, I'd say middle of the road, 95% confidence interval or 0.05 significance level alpha is not a bad choice. If you wanted to be creative, you could pick a 0.06. There's nothing wrong with that number. But for some reason, as humans, we like round numbers like 0.05, and that would be more likely something we'd see. So we'll pick a 0.05 in this problem. The other problems I have in these notes are going to straight out tell us what it is, so we have to pick it out of the context. So that ties in with what we have here, making a decision after we get a p-value. So the next thing to do is write out both the null and alternative. We're essentially at this part right here. We need to come up with the unknown parameter using the context. So that's what this is referring to right here. We'll be underline it so we don't have this getting too busy. It's going to be P because the data is categorical. We'll say P equals the population. You could say proportion or percent. I'll go with proportion. This is success failure data, so we'll mention the successes or the population first, your call. I'll keep it in the same way we've been doing it all semester. I'll mention the successes. We'll say the population proportion of, I'll abbreviate to just marijuana users. And then mention the population. It's specifically 18 to 25-year-olds because that's where our sample came from, among all 18 to 25-year-olds. So this looks like this is United States national data. You could say the United States of America, or just leave that implied based off this information that was given right here. So we have the parameter P. Next thing we're going to write down is the null hypothesis. H naught involves P. The alternative hypothesis, HA, involves P as well. We always set equality in the null hypothesis. But the alternative, it depends on the test, what they asked for. If they said has increased, we would have put in a greater than sign here, less than sign for has decreased. But if they don't say anything specific about direction, if there's just no keywords at all, we put not equals, the default test. Then the final thing is that hypothesized value, which is going to control essentially all of our formulas. Half of our condition checking is the historical data. The null hypothesis is the statement that nothing has changed since year 2000. It's been 25 years and 13.6% of this population are marijuana users, is what the null says, but we put it in as a 0.136. So there it is. The statement of not guilty, the statement of the status quo is the same, no change whatsoever. But as researchers, the reason this study was conducted is because we're looking for a change. So we are just trying to see if we have evidence that P is not equal to 0.136. So that value P naught goes in those two locations and so many other places as well. We haven't even calculated P hat, but this gets us started with the toughest part of this problem, both stating the parameter and putting down hypotheses. Well, any questions at all, folks? Okay, this would be a perfectly fine way to write this out on a quiz or an exam setting. But if you want to make this a sentence, it flows kind of nice. You could say, here's your parameter, and then just make a command. Test, the null, P is 0.136, against, or you could say versus. The alternative, P is not equal to 1.36, at what benchmark of evidence? Alpha equals 0.05. This is a nice way to write it out because it puts everything in one line. And this is where you're going to come back to almost for sure on this line. We have the parameter above. So we'll refer to this again when we go to make the conclusion on this problem. First, let's do some condition checking. I'm not going to ask for condition checking on the quiz or the final exam. It's going to be more focused on the mechanics and conclusions. But for the sake of the homework, we'll check them here. First condition that we check is randomization. So here's condition 1. We're told we have a poll of 1,283 randomly selected 18 to 25-year-olds. There's a lot to be thought about when it came to that randomization. If it's national data, they might have gone for a simple random sample, but that would have taken a lot of work and effort. They might have taken a specific sample amongst states. They might have been doing a clustered sample in a certain sense. But if it's just telling us randomly selected, we at least know randomization did happen. We look up on the conditions, they ask for a simple random sample, a higher level of rigor in the randomization, or some indication the sample was representative of the entire population. Here, we'll mention what we see. The study did randomly select the participants. So in that condition, we have a pretty nice outcome here. It leaves a lot to wonder. If our conclusions are completely sound, we'd have to look in more. How exactly did they randomly select the data? But that's at least a good signal that it wasn't just conveniently sampled in some weird way. Condition 2 is tricky. Pulling up section 13.3 just as a reminder of how tricky this gets. In 13.3, this is what we did for typical problems. The number of successes, this was in the sample, was 173 in one problem and 851 in another problem. And this was in a problem where this was about surviving some weird form of cancer, 173 survivors after 5 years. But we do something totally different in our problem. Even though we have 205 successes, that's not how we do this computation. It depends on what you said in the null hypothesis and what your sample size was. So let's write this out carefully. Even more carefully than that, let's change this to if H naught P equals 0.136 is actually true, I'll just say is true, then here's what we're going to calculate here. It's the number of successes we would expect to see in that sample size before we even conduct the study itself. And you would know the sample size you're likely to get in most cases. So this is a condition you can check even before you go to gather data. So then expected number of successes equals n times P naught. So if this value was crazy, like say 0.0001, the weirdest null hypothesis ever, this condition might not actually be met because that value would be too small relative to that as a sample size. But we had a reasonable value. We just used historical data. So this is going to be n for 1283 times P naught, 0.136. So it looks like this condition should be met. We have to compute and say what this value is on paper. So 1283 times 0.136 gives us 174.5 if we round successes. And it's weird to round, right? You can't have really a half a success. That would mean a half of a young adult that is a marijuana user. But the reason we really keep the decimal number is it's about expected successes. If we repeat the study over and over again on the same population, making the same statement of the null hypothesis, then that's the number of successes you would get on average. Because it's an expected value or an average value, a decimal number is appropriate for this kind of problem. But this is what it had to do. It had to be greater than or equal to 10. So we have a pass on this level. Then we go expected number of failures equals, we can just take the number we just found, 174.5, go n minus that number, 174.5. We've used that trick quite often here and there in the last sections. So let's use it again. I guess I should write out what n is. N is 1283 minus 174.5. This number comes out as 1108.5. It's also greater than or equal to 10, the value we had to exceed for the central limit theorem to work well. And so this together tells us the sample size is large enough. Are the conditions fully met? Well, that depends. There's still a question, an open question on, is the data independent? There's another question about, is the sample in excess of 10% of the ordinary population size? Probably not. There are millions of 18 to 25-year-olds, so that's almost certainly going to pass. But these are going to be the two major questions that we would focus on if this came back as a quiz problem. Kind of mirroring what we did, say, with confidence interval problems. Only difference is watch out for that P naught value to get the expected numbers just right. Well, that's the hard work. Saying what the parameter is, forming the test from the context. Everything else is just write down a formula, compute it out. So we're in the mechanics portion of the notes. Any questions or comments at all, folks? Getting through the tough parts? Okay, I often think of this as now kind of the fun spot because it's hard thinking getting through, especially part A, but everything else is, if you know the formula, say if you put it on your review notes for the final exam, you're in great shape. When it says test statistic, you just have to write out, well, what is the test statistic specifically? It's Z equals, let me highlight that differently. The test statistic is Z equals P hat minus P naught divide by this dangerous object that we'll calculate separately, standard deviation of P hat. And I'm sensing the need for a new page, so let's drop it down. So first, before we go to calculate anything, let's focus on how about P hat. We haven't even calculated what that was yet. P hat is the number of successes in a sample divided by the sample size. So it's successes divided by n. Our successes was 205 in this problem, so that's the numerator. The sample size n was 1283, so we could have wrote P hat right here as P hat equals 205, 1283 if we chose to. Let's put it down here. 205 divided by 1283. Here we have to be pretty careful about rounding. This goes back to the question you were talking about at the start of class, with MyLab statistics being pretty particular about their numbers. If it says round to 4 decimal places, it means the final computation to compute Z. Let's round everything else to a minimum of 5 decimal places, 6 if we want to be just a little bit extra careful. I'll go with 6 just for erring on the side of caution. So 205 divided by 1283. Gives us to several decimal places of accuracy, 0.159782. Okay, we've got it rounded. This is a good time to compare it to the null hypothesis. The null hypothesis said 0.13 per 6 as a proportion of marijuana users. We're saying, that's close to 0.16, right around the neighborhood of 16%. Looks like it's gone up, but the full story will be clear once we know the standard deviation, the error in the measurement for P hat. So let's go to the next step. Standard deviation for P hat is this formula, and it's this pretty sketchy one. Let's be careful with it. It's square root of, muscle memory is going to tell you to write in P hat. I mean, that's not necessarily bad. That would mean you learned the confidence interval procedure really well. That's this up here on the top of the notes here. But if it says something like SD, it really is a whole different formula. Standard error is the approximation to the standard deviation, but we know the exact standard deviation. Under the assumption the null hypothesis is the actual truth of the population, we put in P naught times 1 minus P naught, divide by the sample size n again. So in this problem, it's square root. Go back to your null hypothesis, 0.136 times 1 minus 0.136 divided by 1283. So we nearly have the standard deviation. Let's round this one to 6 decimal places as well. Let's clear the calculator. And just as a reminder for kind of a fast way to punch this in, put in 0.136 first. Let me try again, 0.136 in first. Then build the square root symbol. Second power 2 for that. You can up arrow, hit enter to paste that in. Parenthesis 1 minus. Up arrow and enter to paste it again. Close the parenthesis and hit division by 1283. Okay, let me know if you're getting a different value. I got 0.009570. How's that look to folks so far? We on the same track? Awesome, glad to hear that. Let's bring that in. So 0.009570. So it's kind of like doing a confidence interval problem, except the test statistic is just a different formula. It's kind of cool to see the z-score formula come back in a certain sense. It just looks a lot more different this time. So back to the original z-score, in place of p hat, put in 0.159. Yeah, absolutely. Then go minus. And notice how many times p naught comes up. It's just over and over again in this problem. So missing that value makes everything else feel impossible. But if it was a final exam question, you'd lose 1 point if you got everything else right, even if that value was off. But carry in for p naught, 0.136 again. Then divide by that standard deviation we just calculated, 0.009. .570. So once we compute that, it will tell us the number of standard deviations that our actual data is away from the assumption made in the null hypothesis in terms of that standard deviation. So let's compute one more time, big parenthesis, 0.159782 minus 0.136. And here's another great accuracy hack in your calculator. Go division by, and you can type this out for 6 decimal places, or you can just up arrow and paste that in, and that's way more accurate now. Hit enter there, and to 4 decimal places finally, my test statistic comes out to 2.4851. Rounding differently might have got us a different number, and I'm not too worried about that on an exam or quiz situation. I'm more focused on the concepts, not how many places you put in here. So if you put 4 places on everything, your number is probably different. But MyLab statistics can be a pain on this, so watch out for that. Go for extra decimal places to get a more accurate end answer down here.
You really think it would be different than that if you only went to say 3 or 4 decimal places on the other 2?
3 definitely, but 4 places, there's a chance it might round out right. That's kind of hard to say, but let's take a look at that. I'm kind of curious now. If we rounded to 4 decimal places, it would have been, let's see, we can do it pretty quickly, just rounding this one to 4 decimal places. It's a 0.159. This would round up 0.1598 minus 0.136. Then divide by, let's round this one in the denominator to 4 places. It'd be 0.0096. So if we rounded everything to 4 places, we get, it's actually off in the 100th spot already, 2.4791. That's definitely a level where MyLab statistics might say, even if you know this concept perfectly, they're going to say potentially your answer is wrong. And that's extremely frustrating in this homework system. Yeah, that's probably what was going wrong before.
Yeah.
I see. Yeah, sorry about that. Well, that's one of the reasons this is tougher than the confidence interval. It's because stuff just kind of feeds into itself and it gets recomputed again. Whereas with the confidence interval, it just sort of went together. If you rounded here, it wasn't as bad because it didn't go into a denominator. Well, we're ready for the next step. Any last questions or comments, folks, on getting that test statistic? Here's where you'd want to pause. This one is another computation. It's going to be using normal CDF, just like if we were in chapter 5, way back in the day, before midterms even. But you have to know, what are you actually going to calculate there? And it all depends on your alternative hypothesis. So this is a good time to revisit that. It was a two-tailed test. Your p-values depend on that one type of test, because this is what it's going to look like. For a right-tailed test, your p-value is somewhere over here to the right of your test statistic. The left-tailed test, it's somewhere on the left tail. But the two-tailed test, unfortunately, the default test is the hardest one, trickiest one to visualize and compute. You double either the right-tail area if your test statistic was positive, or the left-tailed area if your test statistic was negative. So let's carry this down into the notes just as a quick reminder that this is what's going on in the very next step. Looks like we're addressing for the 3 alternative hypotheses, the trickiest case, but that's okay because this is, again, the most important test of them all. The default test is the two-tailed one. So when it says calculate the p-value, first thing I would do is draw a graph. Here it is. When we standardized, we actually changed the mean to 0. Then we changed the standard deviation to 1. This is shifting and scaling the data. If you remember that not so fun section in chapter 5, this is where it comes back into play. Minus subtracting this shifted the mean to 0. Dividing by this standardized the standard deviation to a 1 now. So here's N01. We place in the test statistic 2.4851. It's somewhere off here, pretty far to the right, almost 3 standard deviations. 2.4851. And there's really 2 tails of area, but the quickest way to compute it is to be sure that to double the area you get right here using normal CDF. So we're matching up the same kind of test we have, the two-tailed test. And here's what we're going to use next. Go to normal CDF. In normal CDF, this is input 1, lower. We have area going to the right, so inputs 2, upper, is 10 power 99. And so now hit second vars. Option 2 for normal CDF. And my lower needs to change to 2.4851. Upper is 10 power 99. Mu with sigma at 0.1 is already set correctly.
Will that always be that?
Absolutely, yeah. It'll always be a 0.1 for every one of the tests, not just the two-tailed. So that's one nice thing, right? One last thing to worry about. Hit enter through these. And here's the easiest mistake to make. We've got a value that's not the right value. When it says two-tailed test, it's actually being pretty literal. There's actually another value here that we have to get its area on as well. But because there's a 0 here, this area is exactly this area. We just double the area once we've used normal CDF. So in your calculator, immediately go times 2. That's the easiest thing to miss once again. And that's your actual p-value. This is so easy to miss, I think it deserves a screenshot for the notes as well. When we made this wording on the notes right before going on an entire Thanksgiving break, this is what we meant. Two-tailed is literal. Doubling the area means you had to do this. And so finally, after all that work, here's our conclusion. The p-value for the two-tailed test is 0.012. We're going to 4 decimal places, so that would be, rounds up with carry, 0.1230. Or excuse me, 0.130. Let me double check that rounding. So 5 there means rounds up. That's a 0. Carry 1 here, so that's a 3.10130 is our p-value finally after rounding. MyLab Statistics is a jerk about rounding too, which is really annoying and heartbreaking sometimes. So any weird things are happening with rounding, don't forget you can also hit the Ask My Teacher button. They'll send me an email and I'll just email you right back. If it's a rounding error, I'll just tell you and give you the value they're expecting. If you're off by, say, a 0.130 and you gave a 0.0129, you know what? That's close enough for me. Well, that's all the mechanics. The last thing to do is the big conclusion.
Real quick, so if it wasn't a two-tailed test,
Yeah,
would you just give that one answer?
absolutely. That's correct. So when looking at the data, this is really bad statistics. But if you looked at the data and decided it should have been a right-tailed test, we could never change the direction of the test, and even after we see the data. But if we suspected it had gone up originally, and we made this a right-tailed test, we'd be using this right here. We would have just taken that value, just like you said. Lower would have been z, and that would have been our p-value. Notice the p-value is always half as much every single time, which means you're more likely to reject the null hypothesis and get a favorable conclusion. That's interesting. The chance of getting your favorable conclusion is a lot higher in the right-tailed test. Why is this one a default? It lowers the chance of making a mistake, a so-called type 1 error. If we had more time to talk about that error, this is a very balanced test. We're not making our p-value super small. We're admitting there's more uncertainty in the problem. It could have gone up or could have gone down, and it made our p-value twice as big. But it's well worth to make that kind of exchange. We go back to this table next. And the fact that we decided it was a 0.05, we chose it ourselves specifically. But if we chose something different, we might have had a slightly different conclusion. If someone chose a 0.01, that's bigger than 0.01, for example, and we would have been in this situation. We would have failed to reject the null hypothesis. We would have said our study did not have enough significant statistical evidence to assert that alternative, whatever it is in context, is true. But as a class, we went with the 0.05, so we have statistical significance. That's kind of funny, right? When we do a statistical problem like this, essentially people that have already decided on their sample size, they've already decided what the alternative hypothesis will be, and they have most definitely already decided on the significance level alpha. None of this can be changed. Even after getting the data, we can't change the test to make it seem more exciting, more significant based on what we collected. So let's go carry this table down. We won't copy paste this table on every single problem, but this is our first full problem with the p-value. So let's put it down here as a big reminder. When it says to give a practical conclusion in the context of this study, first we have to decide on what decision we're even going to make in the first place, and that's based off the p-value. Let's write it in right here. I'm going to put it in orange just to make it be a comment. We can say, since the p-value equals 0.0130, and that is smaller than 0.05, which is equal to alpha, a value that we all set as a class, significance level alpha, we are in that land. We have statistical significance and we will reject H naught. So that's the decision we will make. Unfortunately, it's not the practical conclusion. We can't report to, say, the media, the public, at 0.05 level of significance, reject H naught in favor of HA. We have to say exactly what all this means. And that makes sense. If this study was a big deal to you, you'd probably want to do that just as a default already. You'd want to say exactly what you found because it's important information. So practical conclusion means pulling in the context, but it essentially just means go to the very top of the problem. This is similar to what we did with confidence intervals. Let's paste all this in as a reminder and convey our results. So here's where we're at so far. Any questions at the moment with getting the p-value or making this decision here in orange? Okay, so we had less than alpha. We're in this land. We'll make that decision. We're rejecting that outcome entirely, which just means we're rejecting the null hypothesis, and our conclusion is this. We'll put a little border here because everything we put in as a screenshot is just tying together in the notes how we make this conclusion. But this is where the answer is going to end, right here. We'll say the following. We have found significant statistical evidence and we want to say at what benchmark. Let's say here in parentheses at the 5% significance level. This is much like when we said at a 95% confidence interval, when we gave a confidence interval problem or result, that 5% came from alpha at 0.05. That something is true. And that something is this right here, that entire statement, P not equal to 0.136. But we have to say what P is. So this was like the most important, very first step of the problem. What is the population? What are the successes? What is the parameter? So we'll say altogether, we have found significant statistical evidence that the population proportion of marijuana users, and we can abbreviate a little bit more even at this step. I'll say of THC users among all 18 to 25-year-olds Now we have to finish that sentence, but we just said what P was, and then that part ends. Like we're being really literal here. We're just saying what we wrote down in symbols verbatim. Is different from, you could say, or is not equal to, you could say. Pick whatever verbiage just sounds kind of nice. I'll go is different from. Point 136. You could have said 13.6% here. Just say population percentage instead, and that would have flowed just right. I think that's kind of a nicer conclusion because I think people, me included, like percentages more than proportions. But the homework sometimes asks for a proportion, so there it is directly. We'll do one where we mention a percentage instead. And that's where the whole problem ends. Again, this is a border here just to say this information was just to help us get that conclusion. We made it, folks. It's a lot of work to do a hypothesis test. There's a lot more extra setup compared to the confidence interval. But the cool thing about it is once you've got the p-value, once you've decided on the decision you make, it's almost the same kind of conclusion as a confidence interval. Just write out what you found is either an interval or as an alternative hypothesis. Any last questions or comments at the moment? Okay. Now imagine this is a real problem out in the wild and it's not in a statistics class. Maybe you're reporting this to, say, the press secretary in the White House. This is really important information. And you told everybody, a cadre of reporters, and they're all taking pictures and they're about to ask you a question. We found evidence at the 5% level that that proportion is not 0.136. Can you imagine what everyone is going to ask you right after? Well, what is it? If it's not 0.136, has it gone up? Has it gone down? What's your estimate for it? What's your margin of error of that estimate? And this is the way these statistics textbook problems are kind of weird, really. This is not the end of the story, it's just the end of the problem. What you would really be doing in a real data is you would immediately do the confidence interval. If you found statistical significance, and even if you didn't, people still want an estimate on that parameter, P. We never gave the estimate, we just said it's not 0.136, and that seems like a joke that's lacking an entire punchline. Well, what is it? You would have to do the whole confidence interval next. But you know what? When you do that confidence interval, it's going to be above 0.136. That's why we got statistical significance. But that's if, and only if, it's a two-tailed test. That's really important. And you picked 95% confidence. If you pick the 95% confidence to match the 5% significance level, your confidence interval and your significance level conclusion will all be the same. And that seems weird. If it's a right tail test, it doesn't work out the same unless you do a different confidence interval, one which has infinity on the upper bound, which we never did. And same with the left tail test. If you do another confidence interval to end this analysis, your confidence interval would have an infinity on the lower end, matching that negative 10 power 99. And we just never did those confidence intervals in this book, so we didn't spend all day in that chapter. But even for the left tail test and the right tail test, the story doesn't just end at the conclusion, you also get an estimate in ordinary real statistical analysis. But because it's a textbook problem, we'll end right here. Any questions at all, folks, on this top to bottom analysis? Well, half of it, missing the confidence interval. Okay, our goal is to do it again. We get faster the more we practice with this, but these are pretty big, chunky problems. If that was our only question to do in these notes, I don't think that'd be a very fair deal. So I have two more examples. You could probably guess one's a left tail test, another one's a right tail test. Some of them will have significance, others will not. So let's see if we can get a little bit into this one. We'll try not to end and break it at a bad spot, but we'll get this started for when we come back on Wednesday. So here's our next context. The paper, Teens and Distracted Driving. So this came from Pew Internet and American Life Project 2009. I need to get some old data. Some of this is starting to look pretty old. Reported that in a representative sample of 283 American teens aged 16 to 17, there were 74 who indicated that they had sent a text message while driving. It's a kind of shorter context. It's kind of interesting about distracted driving. This is apparently ungrammatical. I'll just ignore it. Does these data provide convincing evidence that more than a quarter of Americans aged 16 to 17 have sent a text message while driving? We'll test appropriate hypotheses at a provided level of significance. So same kind of problem. Let's read through this again. The moment it said sample of and a number, that gave us a sample size. The sample size is 283. They're American teenagers in the range 16 to 17. I think in Idaho you could drive at 15, so that kind of says something about the study. There were 74 who indicated they had sent a text message while driving. Absolutely good call on that. That seems to be what the study is all about. So we should call that successes, as you said. So we can now have a number of successes, 74 successes, which means you also have a p hat value. Let's write it in this time. P hat is 74 divided by 283. I'll leave it like that and round later on in the notes. So what else can we see here? I never saw a hypothesized value whatsoever on the first paragraph. It just gave us the study information right away. But notice there's a question mark right here. That means this sentence is probably the alternative hypothesis. Does the data provide convincing evidence that more than a quarter of Americans in that age range have sent the successes again, a text message while driving? There's a hypothesized value in this, but it's kind of hidden. It makes it a tough problem, especially if you saw this in MyLab statistics. Sometimes ordinary language is just not very helpful, the way we say things. I like to see problems where it just gives me, say, for example, a percentage like that's a pretty nice giveaway. That's a hypothesized value, but that's missing in this problem. Yet it's there somewhere. Is anyone able to dig it out?
I would say something to do with the successes in the sample size.
Not necessarily. The actual successes you got in the sample sometimes can be very different from the hypothesized value itself. Something else has to come out of either the earlier context, but there's no hypothesized value there, or the next part, the actual research question, this part highlighted, that gives us that hypothesized value. And it's really well frustratingly hidden. Anyone spot it so far? Good eye. It's that quarter right there. Now imagine how frustrating that could be as a problem in MyLab statistics. When it said more than a quarter, well, what's a quarter? That's a fourth, or 25%, exactly. It would have been nice if it just said more than 25%. I think it's a better way to write an exam question. Exams are usually more direct like that. I'm not trying to trip you up. But if you do statistical work for just a random person, they're probably going to say it like this more often than not. If 25% is the hypothesized value, there's a good chance they'll say it this way. So that's a 25%, which means the hypothesized value is really 0.25. Kind of nasty in a way. Does that make sense to folks? Awesome. So watch out for tricks like that. At the same time, there's more going on here. The other big buzzword is when they said more than. That's indicating a right tail test because that's a direction of greater than. So our test is right tailed, which means in the alternative hypothesis, we'll use a greater than symbol, all because they said more than. They said less than, it'd be in a left tail test, and they said different from or not equal to. That's the two tail test that we just ran. So it says, does these data provide convincing evidence that more than a quarter of Americans in that range have sent a text message while driving? Test our appropriate hypotheses using, watch out for this. A symbol like alpha equals 0.01 or 5%, like in the last one, isn't always something that's baked into problems either. This is something we do have to watch out for in quiz problems, final exam question as well. We have to know when they say level of significance or significance level, either way we're saying it, we're meaning alpha equals 0.01. If they said significance level of 1%, we'd have still made it to 0.01. We would convert it into the decimal number. So we haven't even started the problem, but that's a lot of analysis already and a lot of stuff to probably read and reread just to make sure we're on the right track. Let's see if we can get through the next parts and maybe end on part A. Any questions with what we've written so far? Okay, so when it says unknown parameter using the context, we mean this. P is going to be the population proportion of, here's the success, sending a text message of while driving. So I'll say people who indicated they send a text, I'll just say text briefly, while driving. And it says American teens age 16 to 17, so I'll say among all 16 to 17-year-old I believe this was meant to be specifically drivers, so those that actually had a license to drive. I'm not completely sure, but I think it's a reasonable assumption. So I'll say year-old drivers. Then once having that down, we can say we'll test H naught. That P equals some value versus some HA. That P is, let's backtrack that equality. That P is greater than some value because it's a right tail test. Oh, sorry, question? Gotcha. I would say the major thing to watch out for is it's got to mention proportion somewhere. Whether you put a P or a mu, I'm less worried about, but it should also be a P. I wouldn't take off points for that part specifically, though. But it should mention the proportion somewhere, as opposed to can't say anything like average or mean or anything like that along those lines. It should also mention what the success was, text while driving, and what the population is, 16 to 17-year-olds. So as long as it hits these parts here and here, not as worried about the symbol on the left, these would be the major things to mention. Absolutely. Thanks for asking about that. So we have a test of P equals something versus something else at alpha equals 0.01. That's our significance level. And the way all this fills in is we bring in that most important value that's kind of rude, the value that was sort of hidden in the context. 0.25 goes in the null, goes in the alternative, and this gets us started. This allows us to check conditions and then do all the other number crunching. Well, I think this is probably a good stopping point for us, though. We don't want to rush through the assumptions in 3 minutes. But any other questions at all, folks, either about the parameter or hypotheses? Okay, well, when we come back on Wednesday, we'll probably spend most of the class finishing off these notes, and we might start off section 15.4, just redoing it all again, but with quantitative data. But congratulations, folks, we're nearly done. So this is the last 2 weeks pretty much, and then a finals week. So if you've made it here, you're gonna make it through the course. Any last questions at all before we call tonight? Okay, well, have a good one. I'll see you all on Wednesday.
Glad that we went over that. I don't feel like I need to come in anymore and get the explanation.
Gotcha. Let me help know how it goes on the rounding stuff as well, though.
I'm 100, I'm 99% confident that that was the issue.
Gotcha.
I mean, I kept plugging in those, I even brought my notes that I was gonna have you sit down with me,
Yeah,
show you like what I was doing, but as soon as we seen that it was that different,
yeah,
Not
yeah.
taking
It's
it
kind of
up.
shocking.
that's exactly where it's wrong.
Gotcha.
When you're plugging in those formulas, it's not. Once you have those values, you know, it's not.
It's just plug and play basically, right? It's just like the other stuff, like the 1.5 IQR rule.
Yeah.
Not really too different.
Thank you.
Yep, have a good one. Sure. Yeah,
So, on here it said 85.5,
yeah.
and then online it said 75 point so and so.
Mhm.
So I was kind of just a little confused. I was like, is it 85.5 or is it 75 or is it because it's different because you're going by hundreds?
The values come from really right over here. So the 52 divided by